Welcome to our video on the Risk board game assignment and graph algorithms. I'm going to share my screen here. And we're taking a look right now at our Risk repository. You'll notice that my Risk repository, the one that we are starting with, the one that is the base for your homework assignment, is based off of this, or is forked from the Go data-driven risk analysis project over here. If you were to click this, you could see their original version of the repo, and they have a blog post over here explaining exactly what they did with it. But it's a full, complete risk game where not only can you play as a human, but they have AI players that play against each other and use genetic algorithms to improve their play. We're not going to go into any of that stuff. Instead, we're going to be focusing on just using this assignment to do some sort of like helper functions for an artificial intelligence that are going to teach it to do some aspects of the game of Risk, but not the entirety of the game. Our learning objectives for this assignment, so again, we're going to be implementing many different graph algorithms, a lot of especially breadth first search and Dijkstra's algorithm. We're going to see how those different graph traversals relate to these real world AI problems inside of Risk, and we'll be using somebody else's complex code. Again, I didn't write the base code for this. It was somebody else. There's a lot of things going on in here, a lot of different components, and we'll have to learn how to navigate all of that. And that'll be the main purpose of this video, is to give you the debugging tools and navigation tools to work with this code. Okay, so some quick background here. Risk, again, is the classic board game of world domination. If you've never played Risk before, I definitely recommend playing a game or two before starting this assignment. There's a free online version here that you're welcome to play. It also has some short tutorials to get you familiar with the rules. The board looks like this. It's a map of the world, and it's divided into territories where each territory is controlled by one player at a time. The color here of each of these circles indicates who is the owner of that territory, and the number inside these circles indicates how many armies they have. In the game of Risk, your goal is to build a very large army and then use that to conquer all of the territories. We for board games, it's very traditional to model a board game as a graph data structure using a system sort of illustrating this picture here. Every node in our graph is a territory on the map, and two nodes are adjacent to each other if the corresponding territories are adjacent. Or we say there's an edge between two nodes if the territories are adjacent. So here, Greenland, for example, is adjacent to these Quebec and Alberta, Ontario. Inside of Canada, also to Iceland over here, and Alaska, adjacent to these Canadian territories, also to Kamchatka way over here. We're going to be using this particular graph here to implement our graph algorithms. I'm going to switch over to our code now and just get us familiar with the repository and what's going on. Take a look inside of here. So I've already cloned the Risk repo onto the Lambda server here. The Risk folder itself, the original version of the repository contained many files. I've simplified that down for us just to these two files here that we'll need for the assignment. And I'm going to go ahead and open them up with Vim using our glob system. So if I do vim star, not star, risk/star.py, then again, what this is going to do, the star is going to match all of these Python files right here. So board.py and definitions.py. And I don't want to match this folder right here. So I'm adding the .py at the end of my glob right here. This is a very common thing that I do inside of Vim in order to open multiple files at once. Basically, every time I go into a project, whatever the main source folder for that project is, I open up all the source at once inside of Vim to start working on it. I'm gonna go ahead and hit enter like this, and actually you can see that there were no tabs created up here. I only have what looks like one file open at a time. Vim by default does not use tabs for opening multiple files. If I do :Q right here, you can see that it still says one more file to edit, and so it's not letting me quit. I have to do :QA to quit. We're not going to talk about exactly how those different files were opened up like this. Instead, we'll just force Vim to open things up with tabs by adding this -P flag right here. The -P, yes, P stands for tabs, and now it opens up things in multiple tabs right here. On the right-hand side, let's go into my risk project like this. And let's see, what test cases do we have here? We have this test_search. Let's go ahead and open up the test_search as well inside of Vim. Maybe if I wanted to be really fancy, I could do a double glob, something like */star.py with the -P over here, and this will open up all three of those files at once. That the first star right here matches either the risk or the tests folder, and then the second *.py matches any Python files inside of either of those folders. This is another thing that I do reasonably often to open up files in multiple folders at once. Inside of the test_search.py file right here, we've got a bunch of these board variables being defined. These are going to be the most important thing to understand for our test cases. So that's what we'll start with. On the right-hand side, I'm going to open up Interactive Python, and we will see what we can do with these board variables. If we do Python 3-i test/test search like this, so we've seen this type of error message before, that we're getting this module not found, no module named risk here with risk.board. We know where this module is. It's part of the current project, but by default, Python does not look in the current project to find Python files that are being imported. And in order to fix that, we have to change this to the Python path equals dot, adding the current folder to the Python path that Python will search through to find files. Hit enter. And now this module not found error goes away, replaced with a new module not found error saying no module named heapdict. This is happening on line 4 in the board.py file. So line 4 in this board.py file right here, from heapdict import heapdict. This is a file that we're going, or a module that we're going to be needing later for Dijkstra's algorithm. So that's why it's being imported right here. In order to get access to the heapdict module, I'll do a pip3 install. Oops, I'll type it correctly. Pip3 install heapdict like that, and now it's successfully installed. Up arrow, up arrow, up arrow. Hit enter, and now we are successfully able to load our test cases and take a look at the board0 variable. At this point, not a whole lot of useful information here because the board variable does not have a good underscore repr function magic method defined, and so we just have the default listed here. Again, the reading this from right to left, the rightmost thing here is the name of the class. So our board0 is an instance of the capital board class, Again, using the Python convention, class names start with uppercase letters and instance names start with lowercase letters. So that lets us name instances, let them have the same name as the class right here. This right here is the module that this class is defined in. So the risk.board module, or the risk folder / board.py Python file, takes us to this class right here. The actual function that's going to be the most useful for debugging is a plotting function, plot board. So I use my slash key inside of Vim to search for this plot board right here. It's in this section of functions, plotting methods. And let's take a look at what this plot board function does. Over here on the right hand side, if I do board 0.plot underscore board like this and hit enter, you can see that I'm getting another error message that we're going to have to resolve here. This error message says no display name and no $display environment variable. It's referring to a shell variable. We know that because we have the $ in front of here. There's this $ display that it is looking for and not able to find. If I come press Control D right here to echo $display, you can see that nothing is defined right here. The source of this problem, the fundamental problem here is that we are trying to work on the Lambda server right now, and the Lambda server does not have a monitor connected to it at all. It's sitting in the basement somewhere, just plugged into a power outlet and some network cables, but no monitor, no keyboard. The only way to access it is through SSH. And so how then can we get one of these boards to display? We want to be able to actually see an image of the board. In order to do that, we have to connect to the Lambda server in a new special way, doing something called X forwarding. I'm going to press Control D right here to log out of my Lambda server connection and log back into my just ordinary laptop. Press the up arrow to, actually let me CD here, up arrow to come back to my SSH login command right here. And now I will add a -X flag over here to the end of my SSH program. This X stands for X forwarding, and X is the system that all Unixes use for displaying windows or information in general to a monitor. On my system, I only have to do -X. For some systems, for security reasons, you might have to add a -Y. The -Y disables some security checks that would prevent somebody on the Lambda server from, for example, reading access to your keyboard and doing like keystroke monitoring. So it's a little bit unsafe to add the -Y, but so I'm just going to do the -X, but you might have to do add the -Y. And once again, connected to the Lambda server over here, CD into project, and what risk ls. Let's up arrow, up arrow, up arrow, up arrow. Let's echo that display. Now you can see that there is actually a variable here inside of the $ display, or there's a value inside of this variable right here. And this contains some information about how Python should be able to connect to my laptop in order to display information. The contents of this variable don't matter at all. It's going to be different for everybody, but the fact that there's something here means that the X forwarding is working. I'll press the up arrow again back to my connecting in here to the test cases, and we will now try board 0.plot board like this. And if everything works, there we go. We're successfully drawing a board up here. In this case, we only have one player on this board. There's only one color here, blue, and the amount of armies in each location is assigned somewhat randomly between 1 and 5. On the left-hand side over here, I'm going to go take a look at the actual test case file. Line 6 right here is defining the board, and we'll have to take a look at this territory here in a little bit. But this is just the corresponding thing to this image over here. Board 1 and all these other different boards that are being created are we're first deep copying the original board, and then we're making some modifications to that board. The set owner and set armies methods are things that are built into the or not, things that are defined inside of this board class over here. If I do a slash, I can find the set owner method, and it's doing some things, modifying some of its internal data to change who's going to be owning that particular territory. So here, if I let's take a look at board 1 now instead of board 0. So let's close that window and change this to board 1 like that. And you can see now that a handful of these territories have 500 armies inside of them, still owned by blue. And down here, way in Argentina, there is a single territory with 500 um, red soldiers inside of it. One of the things about this territory or this map, what that will be useful, is if we were, say, the red player right now, we were Argentina, and we were trying to take over North Africa over here. For some reason, we really want to take over North Africa. Then the shortest path that we have available to us would be going from Argentina to Brazil to North Africa. But this is only shortest in the sense that the number of territories that we're traversing is short. We go traverse between 2 territories like this. But the fact that there's this huge army right here means that this is not the most efficient way to go to North Africa. And in particular, it would be more efficient to go around. One way that we could go around is coming up here and then through Europe and down here, but the Europe also has this big wall of 500 armies. And so what's actually the most efficient way to get to North Africa would be going from Argentina here all the way up and around and down like this. So this board is designed specifically to test your implementation of Dijkstra's algorithm and the test cases down below to make sure that you're avoiding these large armies when you don't have to attack them. Let's close out of this. At this point, maybe that was going into too much detail too soon. Just some various different modifications of these boards, all somewhat modifying these original boards a little bit, but being very similar to each other. And let's see, the last one of these, boards 0 through 4 are all just variations on the same board 0 with I don't know, minor changes to them. Board 5 down here is something that's totally different, a randomly generated board with a handful of different players and army sizes here. So with all these different boards, we'll be testing our different graph algorithms on them in the test cases down below. Visualizing the boards here will be very important to do as you're working on these problems to understand why you are or are not passing those test cases. Okay, let's see. So this territory thing, let's take a look at that over here in the board file. GG, come up to the top. We can see /TERRITORY right here. Line 12 is where the territory is being defined. And it's doing something called a named tuple. What is a named tuple? In Python, a named tuple is just a simple way of creating a class that has no functions inside of it. So this territory function, do I have access to it over here? I do. Do that. It's this class. You can see that even though I use this named tuple, or the code uses this named tuple function imported from collections up here, this is built into Python. Even though we're using the named tuple sort of constructor here thing, it is actually a class that is the territory class right here. And in the name tuple, in this list over here, there's 3 elements: territory ID, player ID, and armies. And these are 3 things that must be part of every territory. They must be defined for every territory. And so when I call the territory function, if I do just something territory like this, then we're going to get a type error here because it wants 3 required positional arguments in its constructor, each of these 3 things over here in this list. So the territory ID will just do a quick example of something like 0, 1, 2, like that. That'll create a territory for me. And now wherever we're displaying the territory, it has a nice repr function that tells me that here's the territory ID, here's the player ID, here's the number of armies on that particular territory right now. What is the territory ID? Well, that we'll have to take a look at the definitions file to take a look at that. In the definitions, we have this territory names over here, and this is a dictionary that maps from the territory ID number to the name of the territory. And so let me replot something like this, plot board. And so if we're looking at Afghanistan over here, then Afghanistan is going to be territory ID 0. But if we're looking for Alaska, Alaska up here, that'll be territory ID 1, and so on. We'll see for debugging purposes here in a second how that's going to be important. The territories you will have to be interacting with. The move is something that we're not going to have to interact with in the assignment, but you can see that it's just defined the same way, that it has all these details information about what are the details of move that a player is going to make. Okay, for our first coding task in here under this path verification, we have to implement this isValidPath function. So let's do a / isValidPath, and I'm going to implement this function, and we'll walk through the debugging techniques here that I use to do this, and then we will, and that'll be, I think, the end of our video. So over here on the right-hand side, let me get out of interactive Python for a second and come up here. Let's just remind ourselves that if we do something like Python 3-m PyTest, it'll run all of our test cases. And you can see there's a handful of test cases here just for checking whether we're a valid path or not. This is going to be one of the more important functions to implement. Again, all of these functions, every time you're working on a project, having functions that just check whether something is valid or not valid is the most important thing to do before you actually implement some complicated function. You need to implement things that are going to help you determine whether your complicated function is correct or not. So here, valid path, we've got 3 test cases that are failing, and because we haven't implemented anything over here. So what is a path? A path is a list of territories that are satisfying 2 conditions. The first condition for all territories V in the list, except the last one. The next territory W is in the neighbors of V. And then no territory is repeated multiple times. Down here in the arguments, we can see that the list must be a list of integers. I'm going to come back into interactive Python, and let's plot board 0 here and take a look at some examples of valid and invalid paths. So the only way that we've done this plot board function so far is with no parameters inside of the parentheses, and that just plots the board like it is. But we can also plot paths, and in order to do that, we add an argument inside of the plot board function, which is the path that we want to pass. Again, a path is going to be a list of numbers. So let's try just 0, 1 here at first and plot that and see what happens. And when we do that, we can see that here is this black line right here. This is the path that was plotted by this function call right here. And so it's saying it's starting at territory 0. Territory 0, again, is Afghanistan right here. I know it's Afghanistan because in my definitions over here, it says that territory 0 is Afghanistan. This right here, this territory is Afghanistan. And then territory 1 over here is Alaska. Alaska over here, Alaska. This is not a valid path, though, because Alaska over here and Afghanistan are not touching each other. So this is not a valid path. And just by plotting this, I can easily see that this is in fact not a valid path. We take a look at the test cases over here, and let's go down, press 35, GG, ZZ to zoom in on the test cases. We can see these examples of valid paths. These first 2 cases are sort of trivial paths with nothing in it or with one thing in it, but then down here we're getting some more interesting paths. So 6 to 34, let's plot that. The test case is claiming that this is not a valid path. So let's just visualize that and see if that makes sense to us. So 6 to 34, this looks like it's connecting China with Southern Europe, and those aren't adjacent to each other, so that is not a valid path. Down here on, let's jump to this path 5 over here. We got a really long list like this, and let's close that out down here, up arrow, and let's paste that list in here. And if we do that, then we can see that here's the path that is going from Mexico over here all the way to Siam over here. Every intermediate step here is visiting a country that is valid or that is a neighbor. And so this entire thing all connected together is in fact a valid path. If we were to delete some of those intermediate connecting countries though, so over here you can see we go 537, 4, 537, 4, and then here it's deleted uh, uh, 24 and 39. This test case down here is missing the positions 24 and 39. And if we delete those, then we will not be a valid path anymore. So delete 24 and 39 to get this last test case down here. And doing that, now you can see it's jumping straight from Brazil here over to, looks like, yeah, maybe straight from Brazil to Southern Europe right here. And so this is not a valid path because these two countries are not connected, even though most of these countries here are connected. Okay, so how do we check to see whether something is a valid path or not? Well, we saw before that there's these trivial cases. Again, if we have nothing in our path, then that's a trivial case where things should be a valid path, or where we should be returning true. So if path, I'll do it this way, if length of path is less than or equal to 1, then return true, that we do have, in fact, a valid path. And otherwise, we need to somehow check whether we are in the neighbors of our, actually do all the hard parts of this function. Right now, the thing that's jumping out to me as the easiest way to do that is, well, let's start by just thinking about a test case of length 2. So here we have 0 and 1, so the next situation would be of length 2. So case of length 2 right here. So maybe that is my example path that I'm thinking of. And what I want to do is I need to check whether the thing at the front of the list here is adjacent to the element over here. And it turns out that built into this this class, they have this list of neighbor methods right here, where we can get the actual neighbors of a territory. So here, this neighbors function says it creates a generator of all territories neighboring a given territory. I know it's a generator because down here it's using the parentheses instead of the square brackets. So it's a little bit more efficient from a memory perspective than using lists to use a generator here. There's not a whole lot of territories, so it's not, yeah, the largest number of neighbors I think is 5, so I probably would have you just use the list here instead of a generator. But the generator is maybe a little bit more efficient here. And then we can loop over those neighbors to see if we're contained in the neighbor. Let's come down here and try that out. So down here, let's say self.neighbors of path of 0, and I just want to print out what that's equal to so that I know what this neighbors generator is going to look like. And so now down here, if I do board 0.is valid path, and then 0, 1, this was just one of the test cases here that we were looking at. And Oh yeah, I've made some changes to my file over here. I forgot to reload interactive Python. That's why we're not getting anything printed down here. So Control D, up arrow, rerun, up arrow, and run that. And we can see that this neighbors right here is printing out this whole generator object. Printing out the generator itself is not super helpful because I mean, you can see there's not actual information listed here. I know it's a generator, but I don't know what's inside the generator. And so I'm going to change this so that it is the list of that at P that I'm printing instead of the generator itself. And there is the result right here. This is, I don't know, maybe a little bit hard to read here still, because what it's actually giving us is the territories instead of the territory IDs. It's not just giving me the numbers like I wanted to see, is this number 1 over here inside of this list in any way? It's giving me the actual territories itself. And so from these territories, I have to extract the territory ID. Okay, let's figure out a way to do that. So self dot neighbors of path at position 0 like this. That gives me this whole list over here. I still need to convert that into a list again. And this we'll call it neighbors equals that. And then let's do a neighbors equals neighbor dot territory underscore ID for neighbor and neighbors. And this is, yeah, that looks okay to me. It's not going to pass the linting, so I'll go ahead and remove those spaces like this. And then let's do neighbors at P, printing that down here. Control D, up arrow, rerun this, up arrow, print that. And so here now we get a list of all the neighbors, actually their IDs over here compared to my path up here. And here I can see that this 1 right here, this 1 is not a neighbor of 0. We've already seen that visualizing it, that Alaska and Afghanistan not neighbors. And so it makes sense that the 1 does not appear down here when I'm looking for the neighbors of 2. I'm going to clean up my debugging output down here a little bit. Again, as I'm programming, I'm always, like, my number 1 focus is on making sure that my debug output here is nice and clean, because I am, this is like my ground truth. This is my only way of understanding what's going on in my code. And so I always want to be focusing on that this is like not just including the information that I want it to include, but that this is enjoyable and pleasant to look at. And right now, this is not enjoyable and pleasant to look at because of this long thing right here. So I'm going to get rid of that. We've replaced it with this thing, which is a little bit nicer to look at. I also actually, I'm not 100% sure right now. Am I looking at, or is this right here, is this the neighbors of 0 or is this the neighbors of 1? It's not obvious just looking at the output down here what case that is. So I'm going to tell myself what I'm looking at here. And let's do path at 0 at P, print that out as well, so that I know exactly what it is I'm looking at here. Path 0, neighbors, there we go. Okay. Again, I always spend a lot of time on just making this debugging output over here really nice and friendly, so that I always have high confidence that my mental picture of what's going on in the code matches what's actually going on in the code. Okay, so the next thing that I need to do is, in this case, I'll need to return false because the 1 here is not contained in this list over here. So I'll have a little if statement of if path at position 1 is in neighbors, then we can return true, else return false, like that. Control D, there we go, up arrow, rerun, up arrow, run that. And now we're getting false here because this is not in the neighbors. That's good. I'm going to, so if I just change this to a, say, 36, I'm picking 36 because that's in the neighbors list right here. Just visually, I can see that returns true. Okay, that's good. I'm feeling confident, like this is starting to work a little bit. And I'm going to start doing another test case here, this one right here. Notice that the test cases over here don't have an example of something with only 2 inside of it. That is a passing test case where it is valid. So I'll have to create one myself. Let's try 5 and 37 right here. I know that this must be a valid path because the entirety of this must be a valid path here. And so I'm just giving myself a little bit more confidence that my code is correct. Again, one of the most common mistakes that beginner programmers make is you don't do enough tests, you don't print enough information, you don't spend enough time just making sure that what your code is doing is what you think it's doing. I go very, very slow as I'm programming because that's going to ensure that I'm not accidentally creating bugs. Because if there exists a bug and I don't catch it right when I program it, it's going to be a huge pain to track that down. I want to catch the bug immediately when it happens and make sure there's no bugs in my code before moving on. Okay, so at this point, I feel reasonably confident that we're working on lists of size 0, 1, and 2, and now we need to make it work on things even bigger than that. My way of doing this, the thing that makes the most sense to me, is to use recursion to do this. And I use recursion in a lot of places where other people might prefer to do a while loop or a for loop. Some people might say, okay, let's loop over this entire list, checking whether it's equal or whether it satisfies each one of these 2 things. I think that's a little bit messier than doing recursion. I can do recursion here with, I think, just a 1-line modification. And what that is that here, instead of returning true, if this matches, instead of returning true, so instead of returning true, if these 2 things are neighbors of each other, we will just remove the first element of the path and recursively call self.isValidPath of 1 colon like this. And now we will right now, my code is checking whether the very first thing is a valid path, or if we're empty in like the base case up here, then we're good. And so this will be a recursive call. Save that. Come down over here. The up arrow. Run that up arrow. Still true. Let's actually plug in a test case right here. And notice that I'm not even trying to use the PyTest to do this. I'm just going to do this manually here so that I have absolute control over what's going on and I can work through things and try to understand it. And here it's giving me true. That's great. Okay. Now let's try this one that should be false right here. And we're getting false. Okay. So now this gives me reasonable confidence that this is probably working, but I still have to run the test cases. I haven't run all of these test cases over here. I've just done a couple things by hand. And let's come over here, Control D, and I'll do Control R for my PyTest command right here. There we go. That looks, oh, that's interactive. So Control R wasn't the thing to do. We'll do that. I want to, yeah, let's go ahead and enter. Yeah, Python 3 -m PyTest. That's what I'm looking for to run the test cases right here. No module named PyTest. What? pip3 install PyTest. Here we go. Up arrow, up arrow. What? No module name. Python 3 -m PyTest. There we go. That was the problem. A whole bunch of things failing here. And let's just do the -k for the valid path tests. And it looks like I have one that is failing here still. So what's going on? Let's check it out. Is valid path 631 6. And so here / is valid path, and we have 631 6 right here. So this path right here contains a cycle inside of it that it starts and ends at the same place. And if we come back over here to my is valid path function, is valid path, then it says here that no territory is repeated multiple times. Okay, so I think I got this first part down, but we don't have this second part down yet. And so how can we fix that? There's a lot of ways to do this. I will choose to do what I think is the simplest, but is maybe um, the not most obvious. So it is simple but not obvious. And what I'm going to do is use the built-in set function, set path. What the set function does, or what the set container does, recall, is that it's like a list, but it contains each element at most one time instead of multiple times like a list. And so if I convert a path into a set and take the length of that, and that length is equal to path, then this means that each element is repeated only exactly once in the path. Because again, the set removes duplicates. And so if we remove duplicates and nothing was removed, then we are, everything is unique. So here in this case, if not that, if the lengths are not equal to each other, then this will turn false because we have a cycle going on and we don't want a cycle. Up arrow, rerun that, and now we're passing those test cases. The code here is a little bit messy for a couple of reasons, and so I'm going to clean things up before moving on. This thing I'm never going to need again. That's too ugly to ever want to print. Let's comment out these ones here, and let's just delete that there, and make sure everything still works. Okay. Yeah, and if we go back into interactive Python, it's valid path. Okay, we're not printing out any extra junk now. We're going to be using this as valid path function all throughout our, or you'll be using it throughout your debugging process and running the test cases. So it's important to make sure we're not printing out stuff that we don't need here. It's also, so we're passing the test cases right now, but this is actually a, we've run into this accidentally quadratic situation going on here, that this runtime turns out to be a in-log-in or linear runtime because of the duplicate removal right here, that this is going to take linear time to do this step right here. And we're doing this multiple times when we actually only need to do it once, the very first time that we call this function. And then in all of my recursive calls over here, it's going to be repeatedly doing this. So I'm going to just be a little bit clever here. I don't know if that's good or not, but I will be clever here and make this not quadratic, but linear in runtime. I'll do that by adding a helper function here, go xs. All of this will be inside of the helper function. And now everywhere here where I was referencing path, I want to reference xs. I do here :s/path/xs like this. What you'll see, I want to focus on line 126 right here. And again, this is the command for find and replace. Find this string over here, replace it with this string over here. I'm trying to find all of my paths over here, refer to xs instead of path. And it's going to take this path right here and substitute xs for that path right there, or that right there. I don't want it to do that substitution, though. I don't want it to substitute in the name of a variable. I only want it to substitute the actual variable names themselves. So I'll press U to undo that, colon over here. And if I put an angle bracket around something, the angle bracket means that this is the start of a word right here and it doesn't have characters in front of it. So this will only find path if it actually is the variable. So it'll only find this path right here and not this path right here. Hit enter and there's backslash and then the less than greater than. There we go. And so you can see it did the replacing there. You can see up here that it did not replace this path because again, the find and replace only by default replaces on the first occurrence of a line, adding the /g over here at the end, replaces on all occurrences on the line. And so now I hit enter and all of my path variables and only variables have been replaced with this XS variable, which is the helper, or which is the variable for this helper function. And now we can call this helper function return go of path down here like this. And this will do the recursion without calling this check up here unnecessarily many times. Save that, come down here, up arrow rerun. Whoops, that's not what I wanted. I wanted the test cases, make sure I didn't break anything with that. There we go, that's good. And now I've no longer have an accidentally quadratic function and I have an actually linear function. For the purpose of this assignment, if those procedures there didn't make sense necessarily, then that's okay. Your code's not gonna break if you have an accidentally quadratic situation here, but it's very good practice to not write code that has accidentally quadratic stuff, because you never know when that is going to come and bite you in the butt in the future. We saw in the past that there have been many security vulnerabilities and performance degradations related to accidentally quadratic code that somebody thought, surely nobody will ever use this in the future on a serious problem, so I don't need to optimize it. And then it breaks a major website like Stack Overflow. Okay, so that's the correct isValidPath implementation right here. There's a couple more of these isValid functions that you have to implement, like isValidAttackPath. And the difference between an attack path and a path is that an attack path, so in the rules of Risk, when you're attacking, you can only move your armies through territories that are that somebody else occupies. You can only go through enemy territories. You can't go through your own territories. And so whenever you're attacking, the path that you're planning to attack through cannot have any of your own territories inside of it. So in order for something to be a valid attack path, not only does each node have to be just a neighbor, but it also has to be owned by an enemy instead of by your own player. There's friendly neighbors and hostile neighbors functions give you the generators of neighbors who are owned by your enemies or owned by yourself. And so in attack path, you can just use this hostile neighbors function instead of the neighbors function to get an attack path, or to check if something's a valid attack path or not. The cost of an attack path is this will be returning an actual number for you, how many armies